So, my server is already booted here, and we are back to discussing synths. So, what is a synth? Well, actually, we know that the synth is a definition of a synth, that is a blueprint from which we can create synths. Synths are actual, let's say, things running in real time and generating, computing audio signals. So how do we create a synth? By providing a name and by providing a Eugen graph function, that is a graph defining the structure of the internal structure of our synthesizer, which is made up of a connection, it is a patching of Eugens. Eugens, on their side, they are basic units provided by SuperCollider that creates signals. What is a signal? It's a sequence of numbers, of values representing a sound, not necessarily representing a sequence. It's just like a sequence of values. Now, then, once we have created our synth, we have to edit. So typically you will use this kind. There are many possible variations and possibilities, but this is the most basic and the one that I always use. So you have a synth, you create this sort of template with a name, and then you start filling up the Eugen graph function. And so let's go back here. We have let's call it pulse. This is a pulse is a Eugen creating a square wave. Pulse are so now we can add this and we can create a synth. Here it is, our synth. Let's kill everything. Now, if we, in order to summarize, if we look to the synth, we have to keep in mind that this, which is the Eugen graph function, it is the core of the synth. It is the description of Eugen interconnection. Now, a Eugen generates a sequence of values. This sequence of values can be calculated at two different rates, typically at audio rate, but it can also be used, computed, meaning updated at a lower rate. A lower rate, control rate, which we write in this way. A control rate is useful in order to save computation for signal that signals that change at a very slow rate, or typically at a sub-audio rate. So we have to keep in mind that after this, in some sense, a sequence of values is generated, and at each sample rate, at each sample, all the Eugens are updated or at least read, and those values are used to compute the final value of the sample that will be output in our case here. So, of course, in a digital system, time is discrete, so we have time intervals defined by sample rate. And we could have something like this, like a generator. Let's see an example. Synosk. Let's call this frac. And we have this is a generator made up sin osc kr, because it changes like 3 times in 1 second. And this is interesting because what we want to do is to directly create something that can be used here. So we can have something like and add. So we can follow now. We will follow the stream of computation. So let's send this again, and let's see now what happens with the synth from a newly defined synth. What is happening here? Now, what is happening here is that we patched these, or better, the signal coming out from here in this place by means of this variable frac. Note that we could do this directly in this way. This is the same. The point is that it is a little bit more difficult to read, and in particular when you start working with SuperCollider, it is better to be verbose, so you have a clearer idea of what is going on. Okay, so back to our initial version. Now what happened here is that this block here is a Eugen, which is updated at a control rate that generates a sequence of values, because audio signals are always sequences of values, a sequence of values that is of numbers, and that represent this kind of shape, meaning this sinusoidal waveform. So we use the waveform as a shape, and this shape is defined by these parameters, meaning that it is repeated 3 times every second. That's the frequency. Now, why mul 100? Well, because we can substantially shape our signals in various ways. In this case, we are not interested in generating an audio signal, rather in generating a sort of shape of values to be used in for the control of frequency. So we multiply by 100. If you remember that our the Eugens typically output a normalized signal -1 + 1, by multiplying these times 100, this means that we go from -100 to +100. So we have a frequency going -100 + 100. Can we use directly this sequence of values here inside? Well, the point is that our frequency will be negative. That it means that it will be, it's a question of digital signals. A negative frequency will be mirrored in positive with change of phase. Now, we will work in a more straight way, and in this case we add to the sequence of values 200, meaning that -100 becomes +100, and +100 becomes +300. So we have a sinusoidal shape. Frac is a signal, a sinusoidal shape, a sequence of values moving from 100 to 300. That's why we get this glissando effect. So the point is that a signal is not necessarily related to audio. It's a sequence of values, and Eugens can be thought as generators, value generators. Now, of course, if we need to send these sequences to our loudspeakers, to our sound cards, then we are interested in creating something that has some audio quality. So our signals must be audio rate and going from -1 to +1 maximum. But Eugens can be used to create every kind of waveform that is of shape to be used as a control, and they can be created at control rate or at audio rate. That's the same. So maybe we want to do something like this, like frac 1, kfrac. Let's call this keyfrac, and our keyfrac is generated by another sinusoidal generator, varying, let's say that this will vary at a very low frequency, like 1 every 2 seconds, and it goes from 2 and 4, -2 +2 +4, from 2 to 6, and here we use kfrac, so we're keep on patching. Now let's see what's going on. There's a mistake, the classic semicolon error I typically do. You see that the glissando frequency is changing, following a sinusoidal shape, because the frequency of the glissando is controlled by keyfrac, so by another sinusoid. So we're patching one unit into another. So you just have to think about electronic stuff, electronic gear. You have modules, they have cables, and we are connecting those modules, that is our units, by means of this cable, which are linguistic cables, by using arguments as inputs. So we use argument as input to our Eugens, and our Eugen, typically most of Eugens, they throw out a single value, single sequence of values. So we have Eugens typically having possibly many inputs and sending out one output. That's what we're doing here. A Eugen getting some inputs here and sending out an output, which is assigned to kfrac, so that we plug it here as an input, multiple inputs, one output assigned to frac, and use it here for pulse, which has many inputs again. We're specifying 2 of the, I think 4. 1, 2, 3, 1, 2, 3, 4. And then, finally, what is output here, assigned to pulse, is going here. So you just follow the variables. Many times you see SynthDef defined in a very compressed ways. So you have to do a sort of reverse engineering, because you have to start from the internal one and going outside. It's also a question of habit, so you need some time to become a sort of expert of these. Now we're writing in a very clear way by assigning variables, which are sort of labels that allows us to pass our signals from one Eugen to another Eugen. The point that Eugen at the end is simply a generator of values, and those values can be plugged into the input of another Eugen. It makes us think about what is this. So what are these fixed values? Well, those fixed values might be thought as, rather than fixed values, as constant signals. So 0.5 can be thought as a signal, but it's a unchanging signal. So just like you are generating a constant signals, like imaging over time, you have a constant like y equals something. So it is always the same. So if you're thinking about everything in real time as a flow of value, the point is that rather than having a line with a fixed value, here we are replacing this line with something changing in various shapes. So the point is that we are shaping time, shaping signal time by means of other signals, so by creating various shapes that can be plugged into. Of course, you need some, well, you need to think about these mathematical aspects, which are not complicated by themselves. But the point is that you have to follow various ranges and connection. So, is there a way to see something? Well, yeah. In fact, we can do. What happens here? Boy. So we can do something like this, and we see the shape. This is the final shape of our. We can appreciate this sort of accordion movement. So, if someone, I suppose you want to test with, these patching things, you want to test with synth, well, this kind of construction can be a bit tiring, because you have to specify every time a name and send it back and create a synth and so on. Is there a way to do this in a shorter way? Yes, and it is typically presented in the help file, so I need to introduce you to this. Now, this generates a sinusoidal signal. So the signal is generated by this block with default values, 440, phase 0, and so on. But if we look to this from a linguistic perspective, this does not make any sense at all. There's a play message which is sent to a function, a newly created function. Now, how can this work? This does not work from what we know until now. The point is that many things are happening behind the scenes here. In fact, this is a very handy kind of writing in which we specify a function. This function has all the features of a Eugen graph function, but you are not forced to add out 0. So the idea is that we can create a Eugen graph function without specifying this block, which is added automatically. Then, when such a function, when a function receives a play message, the interpreter interprets this as a Eugen graph function to be in which an out Eugen is added. The Eugen graph function is compiled, sent to the server with an automatically generated name for the synth, and then also the interpreter waits the synth to be compiled and creates a synth for you. So all the things that we've done right now are automatically generated here. And so this works, and if you look at the post window, you will see that you get a synth like we did before with a strange name here, which is temp _2. Because actually anytime you evaluate a function like this, a new synth must be created. There's no shortcut for this. But as we haven't provided a name, the name is created by using temp _, and a number. So a new synth is created. So we are a little bit polluting the namespace and memory, even if they are short blocks, so we are not wasting memory. But we are creating a new synth on the fly. Here you see that's the same. We could say, yeah, but actually the server cannot know this. So here we got temp _3. Every time we create a new synth and a new synth. Now this kind of shortcut is very handy because it avoids you the necessity of creating a synth, providing a name, adding the out block, sending it to the server, and creating a synth. You can do it on the fly. And this is quite helpful because maybe you want to understand what is going on here, and you can just try and see. Maybe like here. Mul 100 add 400. You can test and see what's going on in a very fast way. Now, interestingly enough, do we get back something from here? Yes, we get something from here. So let's see this. Right, so what is X to which this is assigned? Well, X is a synth, so we can free this from here. So if we add arguments here, like we say 2, argf, this means that fr, let's call it frequency, as this is an argument, is 2. We are using it here, so this should sound like before, but we can do something like this, x set. So we can create on the fly synths. There's a typical technique for live coding, can be quite powerful and handy if you are improvising. More structured projects typically are better suited by this. So you need a more structured approach. You know you are going to work with that synth by debugging it, having it working and testing, and you create a synth on the fly without adding every time a new synth, like we were doing with this kind of syntax. Now, speaking about shortcut, interestingly enough, if you have something like this and you're experimenting, you can also use scope on this. What happens here? Well, the point is that we are creating a new synth with same feature and so on, and also adding a scope window. So we're getting automatically, oops, sorry, something like this. This also works for frac scope. So if you're curious to understand what's going on spectrally, here we are. maybe sometimes you want to inspect what is going on without having the signals plotted in real time, rather to understand the shape. And well, in this case, what is interesting is the shape over time, but actually, because at the end it's just a sinusoidal signal, but at the end you can have a plotting of the signals, which is very interesting. In fact, let's consider this. Rather than modulating sinusoidal, we can modulate a square wave, and here we are with our plotting function. Now, by the way, there are some interesting aspect here. We are using autocomplete function. Duration is, so we are plotting how much in terms of time. We're plotting 10 milliseconds, but if we want, we can plot something like a tenth of second. That will require a little bit more. So we can, now here it is interesting because if I can drag this, because we see the modulations aspects. So you see this is a tenth of a second. Well, of course, you can plot more if you want. In our case, it's not so meaningful because everything get, how can I say, squeezed into this half-second block. Now, sometimes, speaking about shortcuts, but it is important, sometimes you'd like to understand what is going on by modulating this, meaning by changing parameters, meaning, okay, in this case we can do this, oops, we can do this in this way, no? X set, FR, but it can be interesting to do this to have a sort of continuous control over the parameters, to experiment with the parameters, like moving your mouse. So actually there are a couple of useful so-called pseudo-agents that intercept the mouse. So here, frequency, let's write it in this way so it's clearer, even it a little bit too verbose. Frequency could be, it's the frec parameter, and we can control these by using mouse X, meaning the width of your screen. Mouse X can only use only generate KR signal, and you can define the minimum and the maximum, meaning that the position of your mouse is automatically scaled. So if you want to go from one extreme of your screen to the other, you can map this range, saying that you want to go from 0.1 to 100. And warp is interesting because it's if it changes exponentially or linearly. For frequency, it can be interesting. So let's see what is going on here. Now you have to bear in mind that I have two screens. It means that my screen is the compound of two screens right now. So I am moving the mouse on the first screen. You are not seeing this. Now it appears. Now, in case of frequency, the lag can be interesting. Warp, the warp, it's much more continuous. Okay, so the same thing applies for mouse Y. That's exactly the same. So now we're using the Y position. from here, right here. Now, these are pseudo-Huygens because they create a control from the intercepting the mouse position. So it is a sort of mixed up approach between the server and the interface. They should not be used, well, you can of course, but they should not be used in a structured approach. Rather, they are quite useful, mouse X and mouse Y, when you're making experiments on value ranges. So to understand what's going on between that part, those values and those other values. And of course, we can do something like this, so we understand visually in time domain, like here. So there are ways to inspect. There are ways to inspect your signals, so you can understand what is going on. So the case of mouse is another case of the generation of signals. Now, what happens with mouse? Well, actually, if you remember that we consider that a constant value is just a signal, what happens with intercepting the mouse is the same, in the sense that there is a process looking at the mouse position and generating a value for the mouse position. So at each sample rate, at each sample, we got to see what's going on with the mouse. Well, it's a KR, it's a control signal, so it will not be updated at each sample, but it will be accessed at each sample, that value. So actually with the mouse, we are creating a sort of ramp interactively, so a ramp signal that we are accessing through our synth, so generating a low value variation, depending on the position of the mouse. Now, there are many ways in which we can create signals. As an example, of course, let's keep on working here. Now we have changed the frequency of this sinusoid by means of pulse. Let's do this. Let's use pulse R as our main generator. So we want to create a square wave. So let's work with frequency, because we can clearly hear this parameter. So let's say we have a frequency. Now we control this with the shape of a square. So we want something going in this way. There is a specific set of Huygens which are dedicated in SuperCollider to the generation of control values. Control values, they change very slowly, so they are low frequency, and typically you have something like this, LF, low frequency. So low F pulse means a square wave precisely created without taking into account some audio aspects that are required to be considered while generating square waves for sending them to the loudspeakers. And so in this case, this low F pulse creates a square wave precisely with that square shape. So if you don't believe me, we can look at this. When you plot a signal, it's always better to plot it with the R method. So that's what happened. That's the shape we are creating. Fine. So let's look at the low frequency pulse help file, and this is interesting. It outputs a high value of 1 and a low value of 0. So in this case, it's always a normalized range, but normalized range typically for audio intended UGENs goes from -1 to +1. In this case, it goes from 0 to 1. So we are half of, let's say, the domain. So LF pulse KR, how many times will this cycle be done? Well, let's say 1 every second. And E phase is just the starting phase. Width means it is the ratio between the upper part and the lower part. So width 0.5 means that they have the same duration. So in each cycle you have an upper part and a lower part, to speak in a very approximate way. Do we have to multiply this? Yes, because we want to control the frequency. So which is our top frequency? Well, our top frequency could be 200 Hertz. Do we need to add something? Well, it depends. If we add 200, by taking into consideration, by bearing in mind that it's unipolar signals going from 0 to 1, you multiply the extremes and you get 0 times 200, meaning 0, and 1 times 200 means 200. You are adding 200 and you are going from 200 to 400. So let's see how does this sound. Well, we can just play it. Why? Because it's the frequency is of our pulse generator. This one is controlled by a precise square wave which jumps from 200 to 400. Now 200 400s, the ratio is 1 octave. So we're jumping between the 2 octaves. And which is this jumping rate? Well, of course, it is defined by this frequency here. So 1 every second. So this is interesting because we're using the shape, the LF pulse precise square shape, to control one parameter. So that's the idea of generating shape signals as time shaping in some sense. Now, what happens if we are doing, what happens if we are adding nothing? Well, it happens that our lowest, the lowest value will be 0 multiplied by 200, 0 times 200, 0. So we have 0, 200, 0, 200. 0 frequency is silence. Each half of a second, we're getting this silence, which is 0 frequency. So that's an interesting aspect because we can use these to create holes in some sense in a certain signals by multiplying in this way. Can we do other kind of general consideration concerning this sort of time shaping? Well, of course there is a whole world which opens at this point because it's the world of electronic synthesis. We will see something in the next video, but this typically requires some years. So actually we have no time, and if you come with some knowledge, you can surely apply this knowledge. What I'm trying to show you is how to manipulate this kind of parameters. So and using some specific supercollider construct. So as an example, suppose we want to create a sort of variation over time, random variation. This is a deterministic signal this is another deterministic signals. Random variation. Well, LF noise, and LF noise 0 creates step noise. It means that you define a certain frequency like this, and for that period, in that case, as the frequency is 1, the period is 1, a random value is generated and it just stays there, so it is kept. Then it will be updated at the next cycle. So let's see the help file, and as you can see, generates random values at a rate given by the nearest integer division, and so on. Let's plot this LF noise so we have an idea of its shape, and this is a step noise, so we are generating from -1 up to +1 random values, and this is the period, that is the inverse of the rate we are setting, and for this whole period the random value is kept like it is kept, what can I say, stable. It's the same for the whole period. So LF noise KR 1 second, and we can do something like our first example. Now in this case, what is happening is that we are generating each second a new value between what? Well, between -200 plus 200, and we are adding 200. It means that we're going from 0 up to 200. Let's add this, so we are going from 200 to 400. 1 second. Now, well, of course, this is a bit dull, but it can be made immediately more interesting because it allows us to introduce the notion of conversion. So let's suppose we want to think about pitches, because we're sounds like a sort of very basic instrument. Can we think about this random control in terms of pitches? Well, as an example, we can think that we'd like to move from middle C up to 1 octave. Now, our middle C is defined by 60. So the point is that we need to go from, we can add comments, of course. We have to go from 60 to, let's say, 72. And we have to map this. How can we do this mapping? Well, in this case, you see that we decided to do by ourselves some maths and multiplying and adding. That's a correct way, but sometimes life can be easier in this way. So lean, so -1 plus 1, 60 and 72. So we're mapping the original domain. This is a mathematical operator that can be applied as a Eugen inside a synth. So it will work in real time, and we're mapping it from 60 to 72. Now, the point is that here we got as output 60, a range of values going from 60 to 72, which are meant as MIDI notation. The point is that here we are eating hertz. So we have to convert this, and we can do this in this way. I'm using a new line, so it's easier to read. We need to convert this as MIDI CPS. Now, let's see if this works or not. Now, first thing, well, this is really too noisy. So let's see if we're getting better. Sorry. Okay, so the point is, can we inspect what is going on here, like with post lane? We cannot use post lane, but we can use pole. Poll is just like going to the server and polling a certain signals. So the signals that is polled is posted on the post line. This is just a debug tool, in the sense that it wastes some CPU. So CPU is not wasted if we are understanding issues, but when everything is running, you just remove poll. Well, not so much CPU, but okay. So you see that we are polling at a regular time those value, and there are some issues, interesting issues here. It didn't sound really like notes. Why? Well, because we are mapping a floating range to a floating range. So we are expecting to have integer numbers in our first idea, but later we are getting the correct range between 60 to 72, but with floating points, because of course there is a floating point domain and there is a floating point codomain where we are mapping those values. So maybe we can do something like this. We can round. So we're using mathematical operator inside on sequences of real-time signals inside a SynthDef. So they're just like Huygens. So let's see if we're getting better. Now we're polling after rounding. And this is good. Now we're using we are using integer numbers. So actually we are walking randomly stochastically on the middle octave above middle C, and we can do this. Our improviser can be a little bit shorter, like faster, not short, faster. No. What's going on here? This is much worse. We can do this in this way. Chromatic improviser. Now, interestingly enough, here we're using this sort of step noise, but can we use shapes that we know to shape pitches in similar ways? Well, actually, what happened is if we're doing something like this. Now we have a sinusoidal shape. This sinusoidal shape make a cycle every second. We are mapping this value as going from middle C. Originally it went from -1 + 1. Now we're mapping it to 60. 60 is down there, up to 72. So we're using this shape as a melodic shape. This melodic shape is performed in 1 second, so it's a bit too fast. Let's see what's going on here. Now, again, we are rounding because we are interested only in like representing our sinusoid on a keyboard. So we need to round those values. Let's see. Now this is very fast, but we can do something like in 10 seconds. Now we're creating the sinusoid over the keyboard. Well, it sounds like a glissando. But let's do this. Well, we want to do 1 second divided by, let's say, every 4 seconds. So that's a sinusoidal melody, a sinusoidal glissando. It's not regular, it's not a ramp. Because if you bear in mind the shape of the sinusoid, you see that there is a sort of, how can I say, roof. it goes lower here. And then, and if you want it video game style, but it was better our first version, like a little bit more discreet. No, better this one. With a sort of silent. This sounds like 8-bit. Because it's discrete step. Those are discrete steps as defined by round here, because we're rounding. So it's just like really moving on a keyboard. So, yes, there are a lot of things to learn in relation to this kind of patching, but there's also a lot to experiment by yourself. So you have an idea, you just test this idea by trying to patch the output of a signal into the input of another signal. Of course, you have to bear in mind a question of ranges. So if you're working with frequency, you should know that you should go from 20 to 20,000, and you just cannot do things really randomly, because you have to, there's a sort of framework, some sort of framework notion you need in order to have something really working. But apart from this, you can really think in various ways and experiment in all the way you prefer. So we saw LF noise 0, and just to tell you, there is LF noise 1, which is a ramp noise, meaning that rather than keeping the value and then updating to the next value, from one value another one, a random one is generated, and a straight line is progressively is created, like a ramp, and progressively created. So rather, if you're working with frequency, rather than having discrete steps, you will have glissandos. So you're creating a ramp noise. It's easier to see than to describe. This is LF noise. And then there is also LF noise 2, which is a different kind of interpolation. So always random values with a fixed rate, generation rate, but in this case we have cubic interpolation, and so you get this software kind of shape as still noise signals, because they are randomly generated but with different shapes. That's the point, working with signals as time shapes. So concerning time shaping, for the moment we have created this simple electronic instrument, and they are generators. So we switch them on, they keep on generating. We can change their parameters by setting the arguments specified by the Eugen graph function. Synth, my synth, set this. Fine. But what happens typically in most acoustic sound is that each sound has a history. So we have what is typically called an amplitude envelope. So sound start from 0, it reaches a maximum, and then it goes out to silence, and it goes away, it dies away. Can we create envelope in SuperCollider? Yes, of course, and we can do them in this way, by means, first of all, of a specific first of all, we can create envelope simply in a way, and I will introduce this way just because we are dealing with signals as time shape. So think about this. Pause. Fixed frequency, 440, we just think about this argument, which represents a multiplier. So if we have a constant multiplier, like this, linear constant multiplier, our signal is always multiplied by 0.1. Fine. But can we modulate, that is transform this? Yes, by applying a signal like, well, like this. Let's consider var L, var line, well, can be kr. Where do we want to start? We want to start from 1. We want to go to 0 in 3 seconds. What happens here? Well, now this, let's use so we're changing a little bit. Now this sawtooth wave has a fixed frequency, but what happens is that it is multiplied by the signals output by this, which is a ramp signal starting from this, going to this in this time range. Maybe you want to see this, because image better than 1000 words, and the easy way is always to do this. So this is line, basic line, it's just a line. So the signal is a sequence of values fulfilling this shape. In this case, the default values are going from 0, initial value, to the ending value of 1 in, I don't know, probably 1 second, which is not plotted, I guess, yes. In our case, what happened is that we have a line going with a different shape from 1, starting value, to 0. Multiply by 0, you get always 0. 0 amplitude is silence in 3 seconds. So now what happens here is that our synth is still active. All this computation is still active, but we are generating a sawtooth signal with zero amplitude. So we are sending out a signals made up of zeros. This results in silence, but properly we are still calculating this. So what happens is that, again, the output of saw is multiplied by line. Line goes from 1 to 0 in 3 seconds. What happens after 3 seconds? Well, by default it happens that it still throws out the last value. So it's 1, 3 seconds 0, and then keep on generating 0. So we're multiplying by this signal. So this means that when we start at maximum amplitude, going linearly in 3 seconds, to 0, and then keep on multiplying by 0. So we have this sawtooth with 0 amplitude, meaning we have silence, but we have still computation going on. So if you see here, in fact, well, it's not that much, but it's still one synth going on with 1%, not 0 and something. So there's something going on. Our point here is that we are creating an envelope. It's a bad one. Let's kill everything. It's not a very good one. Better should be this one. And we have to do something like this. This is an exponential value, x line. So you want to plot it? Let's plot this. Well, it would be better to plot this for 1 second. So you might appreciate that the curve is not a line. So let's see if this, well, it's a little bit more interesting. Sounds better. The general point doesn't change much. What happened here is that we are creating an envelope by meaning of a signal. So every time we create a shape and use it to multiply a signal, we are creating an envelope. But of course there are some ways in which we can create a straight envelope like we're thinking about originally. So the point is that we have a class which is called env. Env is dedicated to create envelopes, and it's a specification for a segmented envelope. The envelope is created in this way by by adding an array specifying levels. Like we want to start from 0, we want to reach a peak of 1, go down to 0.5, keep on a straight line sustained for 0.5, and then going down to 0. So we're specifying only breakpoints. And what happens is that we have to provide another array which specify the duration between points. So how much time between these? Well, let's say 0.1, we're thinking in seconds. How much time between these? Again, let's do this 0.1. How much time for this, which is our sustain phase? Well, let's consider something like 1 second maybe. And final release, let's say 4 seconds. So by this we are creating an instance. This is env-new, of course. We're creating an instance of an envelope, and we can use this. This is just an abstract shape. It's not a signal. It's an abstract shape to be used to generate a signal. Do we want to see this shape? It's easy. In this way, this is the shape, a bit unbalanced shape that we have created. So as you can see, the number of elements here in times is -1 in relation to the first array, because we're specifying the internal inside couple of times. This is a very abstract shape. So this is just a way to create shapes. Typically you think about env class as generating amplitude envelope, but in reality it is a possible way to create every kind of shape you're thinking of. By the way, this is a linear, points are connected by means of linear interpolation, but the other parameter is exactly curve. So we can specify this by means of number and 0, or by means of symbols. 0 is this, so our default linear interpolation, while 1 is this. You see, something is happening here in these points. And then we have 2, which I think it's step. No. Oh, maybe. Oh, okay, let's take a look at the help file, so I'm not telling you wrong thing. Okay. Okay, no, I made a mistake in the sense that you should use symbols while you're using numbers. It's a curvature value for all segment. 0 meaning linear. So let's do this directly by step. It's clear. What happened is that rather than interpolating between values, where the value is kept. The value is kept until the new one is to be applied. So there are many ways in which you can create shapes. Now the point is that we are creating a shape, but creating a shape is not enough. We want to create a signal, and this must be inside synth. Otherwise, yeah, we can work it language side, but we want to have it into a synth. How can we do this? Well, it's pretty easy, because this can be used directly inside synth, and we could use this directly instead of var in order to create a signal, a control signal from this envelope, we have to use the Eugen mgen. Mgen is the generator of envelopes. It means that it takes an envelope as a shape. So you go to mgen, you give it this shape, and it generates for you in real time, because the shape is not in real time. It generates the signal that is a sequence in real time following the shape. It's just env is just like again a blueprint, while mgen is someone drawing in real time the line. So here we have as a first parameter envelope. As you can see, there is also gate, which is a word for me a little bit mysterious, in the sense that it's a trigger at the end. So if you want to trigger this, back this envelope, you can. And then there is level scale, level bias, which is not very interesting, and time scale. Level scale and time scales are multipliers to be applied to respectively to level and to times. So what is env? It's an abstract shape, and the ranges of its values, be them in relation to levels or be them in relation to time, can be scaled, compressed, stretched, compressed, and so on. So what I do typically is that I work with envelope in a normalized way, meaning that typically the total duration, I'm working between 0 and 1 typically here. And here what I'm doing is that I am considering this, the sum of all these times should be 1. This is easy, because this means that this is it's a time, and it's the 10% of your total time, and this is the 40%. Now here I have not been compliant to what I'm saying, but the point is this: if the sum of these is 1, the total duration of your envelope, by using these fractions, it's easy to understand the percentage. And then I scale everything here directly inside mgen. That's just a design approach. You can do whatever you want. So now we have an envelope signal, and the easy way to apply the envelope signal is synask. Let's use so r fixed frequency mul is env sig. So we're using env sig as a multiplier. Now beware that we are always working with just with numbers. What is going outside here is a sequence of values. So another approach, which is exactly the same, is to do this direct multiplication. That's the same as before. Well, it's a really bad envelope, but actually it doesn't do what a typical attack decay sustain release envelope does, but actually it is working. So by the way, env class provides you some interesting constructor method like this. This creates immediately a percussive envelope. So if you're lazy or you like this kind of envelope, you can do directly this. So you can use perc to generate a percussive envelope. So now we have changed our shape. Yes, you're curious, we can do this. This is our perc shape. So we are applying this shape using this shape to create the envelope generated by envgen and applying to saw. Let's see what's going on here. Well, that's an interesting percussive envelope applied to our sawtooth waveform. So the point is, what is happening now? What is happening now? We have applied our envelope and the sound is finished. That's our idea. You do this, sound is finished. Fine. Let's do something different. But the question for the server is, okay, I have generated the signal for the enveloping an audio signal as you asked me. Now what I have to do, because we haven't said stop. So what happened here, just like what it was happening for line, is that our envelope generator keeps on generating a value from the last value of our envelope. As the last value of our envelope is 0, it keeps on generating 0 values, and it keeps on multiplying these by the last value generated, which keeps on being generated, that is for 0. But actually our synth is still working, as you can see here. Now the point is that if you're generating a lot of these events that sounds like sound events rather than like an instrument, you have to keep track of the synths that are at work. Means we are evaluating this another time. Okay, a new sound, fine, but now you see that we have two synths, and if you want to have another sound, we're not just having a new sound, we are adding a new synth, which is permanent. So it's still here. So you have to keep track of the synths you're creating. While this can be, of course, can be done, an interesting point is that what about having automatic destruction of synths once the envelope is finished? The ratio in this automatic destruction is that once we have created a certain time shape, or once a certain behavior has happened, the synth is destroyed. And this is very useful because many times there is a sort of history of your sound generator, and when this history finishes, you don't want to keep track of your synth. So you can see that there is a doneAction argument. Well, you cannot see, but if you autocomplete, you will see that one of the arguments, there's my face right now, one of the, I can do maybe this. The last argument is doneAction 0. doneAction is exactly an argument specifying what should happen once that the envelope, in this case, so a certain behavior has happened. In our case, the envelope, the end of the envelope has been reached. So doneAction 0 simply means that nothing happens. The synth keeps on working. doneAction 1 means that the synth containing that eugen is put in pause, just like playing pause, just like evaluating synth run false. You remember that line. While well, there are a lot of doneAction possibilities, very complicated ones, but we are interested in these three. Nothing happens, paused synth, not so much used, and third is interesting, like nothing happens, like the first and the third. doneAction 2 means destroy the synth containing this eugen. So doneAction is like self-destruction. doneAction 2 is like self-destruct yourself. So in this case, if you evaluate this and you take a look on what happens here, down here, you will see that a synth is created and then it is destroyed. So now there is one synth, and now again 0 synths. So auto-destruction. Let's consider what happens with line. take a look at the line help file, you will see that there is also in this Eugen, which is typically used for envelope-like behaviors, that there is a don't-action argument. So every time there is a sort, all the Eugens that in some sense are designed with the idea, a certain idea of a sort of path from start, from beginning to end, typically they are given a don't-action argument so that you can understand what happens when the intended behavior is finished. So in our case, in a case of an envelope like this, of course, there is a sort of natural end. What to do at this natural end? Well, if you want to retrigger the envelope, you have done action 0. But if you want to destroy the envelope, you can have done action 2. So you might ask yourself, why should I destroy a synth? I'm doing such an effort to create a synth, and now this synth self-destroy itself. No, and the point is, so suppose I'm thinking about a synth like an instrument, a synthesizer, like a keyboard, and so on. Why should this self-destroy itself? I cannot control it anymore. Yeah, that's the point, because sometimes you want to have an instrument to be stable. It just stays there, and it has knobs, and you can control them by means of arguments. But sometimes you want to think in terms of sound events that happens. They start and they finish. So this idea of done action 2 versus done action 0 is in some sense the difference between sound event and sound instrument. And the interesting point is that these two very different ideas concerning sound, they can be defined in the same way, and you can switch between the two simply by defining this don't-action argument. So let's see an application of this kind of logic, which is very interesting. Let's create a synth, and our synth is called pulse, and I'm always creating a sort of template. We need arg frec, a frequency, like let's say 100, amp, let's say 0.1, and that's fine. And then we do something like out. I don't know, let's out is 0. So we create var p pool its pulse r frac. Then let's consider mul. It's well, there are various approaches. One is this one, and the point is that we are multiplying this directly for, so we have a square going from minus amp to plus amp, because we are scaling the normalized range for amp, then multiplying this for env gen kr, that's the same, env perc, so directly creating and using env perc, and done action, we're not scaling anything because we are scaling the signal before by means of amp, so it's already scaled, but we are applying just an envelope in this way. Done action 2. Now we need to throw out this by means of 0, no, by means of out pull. So the pull, let's call it pull, the square waveform with a certain frequency and a certain amplitude, it's scaled for with an percussive envelope. Done action 2, each time this is applied, at the end of its application, the whole synth is destroyed. So the point is, when do you set the parameters? At the beginnings. At the beginning, the time you create the synth with certain parameters that they are applied, and then the synth goes away. Now let's create a synth. Oops. Let's create a synth like this. Pause. Oops. Pause. And now the point is that I think we haven't done before, because we were setting the arguments later. We can create them on creation of the synth. So we start the synth with certain argument. It can be done by using an array, and the array is filled with name, like frec, and value, like let's say 200, and like amp 0.2 and out 1. Oh, there's something wrong here. Let's see what's going on here. I know there's something related to maybe interaction, so you know it's fine. So you see, okay, and we can generate a new event with a different value, or like this. So the point is that we're generating a sound event with certain parameters. Now you might appreciate the fact that I haven't done something like this, that is associating to Z my synth. Why? Because my synth is created and it automatically die away. So why should I assign this to a variable, considering that after 1 second my synth would be done? So typically you just create the event, because it's not an instrument. You have an instrument, you have your instrument, and you want to control it over time. Here we're creating events. Now you might say that, well, yeah, fine, but every time I have to create by myself instrument. Isn't this pretty useless? No, because we know some interesting construct like this. We know what is a routine, and now let's do something like of an installation infinite times. Of course, it's always interesting to have something going on forever. Infinite times do what? Well, actually, we just add this, and well, this works by itself, but it's not so interesting. Let's consider that we can declare some variables here, like frec, amp, and out. And every time we generate a new event, we say that out. Well, it's pretty simple, because in our case, what we can do is 0, 1, choose. This is really random. Amp, let's do with frequency. We can do something musical, as we let's go from let's do this array series size 3 octave, start from 48, step 1. If you see, this will give you the sequence of elements 48 up to 83, and the point is that we're creating this and choosing. Now, do we want to be, well, let's keep it in this way. Fine. Now let's consider amplitude. Well, we have discussed conversion between pitch and hertz. The same thing applies for decibel. I think we've seen it. So let's do something like minus 30 around. Let's go to 0. And okay, dB amp. Now here what we are missing is a MIDI CPS, so we can do this directly with frec, with amp, and with out. Don't get confused. These are names defined in our synth. These are variables defined here. So we were missing a crucial point, like, do we want to wait some time or not? Well, maybe it's much better if we wait some times, and we can decide to do something like this. Well, we can do something like this if we want. Not really we select 3 times and choose one of this duration and just wait this duration in seconds. Looks like it's fine. Okay, no, it's fine. Okay. It was some like surprising because it was a long time because I omitted the dot here, so it was choosing in 3 seconds, which was quite poetic, but I was a bit surprised. Okay, so of course we got a lot of variation in terms of pitches in this case and of amplitude, but that's fine. We can have something more. Oh well. Okay, where am I? Here, like minus 10, or maybe we can, rather than use these, use a sort of mode like like 0. Well, we were bound to 0, 3, 5, 6, 7, 10, and here we had something like 60. So here we have 1 octave, a sort of, let's call it blue scale. Okay, there's something wrong in here, like yeah, it's plus, not times. So the point to be appreciated here is that we're doing something like our music black box. What was happening with our black box? That we were doing something like this. Actually, this, quite strangely enough, it works. And we know that. Now, what was happening here? Well, there's a specific construct which is a dictionary. Actually, when you call play on something like this, there's a whole process behind the scene, just like the one we saw, function play. So at the end, here there is a synth and there is a synth, as usual. The point is abstraction layer. Abstraction layering as an operation is the possibility that you have with a language to create on top of other layers more simple and abstract layers. Now, if you think about this works exactly like we've done before while introducing routines. In this case, we're using directly a synth. We have created our own synth and we are creating our own parameters, but you will see that this resembles quite strictly something like this, because that's the idea. This kind of syntax creates an event implemented as a synth with a done action arguments. And so of course here you can do whatever you want in terms of sound generation algorithms that creates something that goes away. So you can we can decide to do this more complex, and we can also do something like this. Suppose we have push and we have so, and we have well, we have to call it so, by the way. Call it in another way. You can call it Bobby if you want, that's the same. And we can have 3 and use well, let's call this it's a sign. And maybe so we have three synth with different name having substantially the same internal structure, but changing their generator. Maybe we can decide that in this case we had some like LF pulse KR like freak. So we had some amplitude modulation here, maybe. Now, if we can also, now if we have this synth, these 3 synths, in this process here, we can say that we have a variable called def, and it can be something like this, like pulse sen so choose. So we're changing the generator. It will not change that much, but still it changes. Well, this is wrong, because now we have to pass as a parameter for synth the name of the chosen. Interesting, in these cases you can also use the counter. Let's call this I, and we can decide that rather than going randomly, choosing here, we can say something like EI, where is it, modulo, this is 3 6, so I modulo 6. So we're working here, and maybe we would like to have something array series from a series of let's say 12 starting from minus 30, and step it's 2. So if you look at these, you see that you got minus 30, 28 up to minus 8. Fine. Then at this point we access I modulo 12. So I modulo 12, it means that first this, then this, then this, and we have a cycle of 12. Here we have a cycle of 6, which is interesting because they are interlocked. And of course, rather than choosing here, we can have I modulo 3. So we're using the counter. Do we have to choose here again, or we can have something like let's do array series size. Let's do something little bit stranger, like modulo 5, starting from 0.1 0.1. Oops, let's debug. Wait, message is wrong, and that's true because we need modulo 5. Otherwise we were asking to wait an array while we have to wait for a number. Ah, yeah, maybe we can also avoid to choose, get to choose modulo 2, and maybe we can go in this way, minus 15, and let's see, this should be something minus 15, minus 4, we got a little bit more volume, so we're bing bing bing. Of course, this process can be also controlled in real time by means of various kind of construct, but let's see if we can complicate this a little bit, like 20 going very fast, and this model should be 20. Now you see that here we're using the size of this. It would have been better to specify this before so that we can access its size. That would be a better way of working, but let's stick to our experimentations. So we're looking fast scheduling. That's not bad. Maybe we can simply do this a little bit more interesting, and that's not what we need to do. We should well, let's do this. Array series, array series 6, esatto, no, starting from 0 and step 12. Then we can have, and we have something like this. Well, let's do this, and then we can have 4 or 3, starting from 2 and going by minor third, and okay, then we can do something like this, and we've got this scale, okay, and we can scramble it, and we say that we can say that frac R is this thing here, then we can say that this is okay, and at this point it's a little bit, but it's not so long. No, I'm not satisfied with this. I'm not satisfied because I want to do something more. Let's do this. 20, and with step 5. Oh, 20 with step 6. Yeah, 20 is a bit too much. Let's do this by, because we reach 95. Let's do this by 10 and 10. Okay. Ah, this is an interesting. Okay. I'm sorry. Now I'm improvising, and of course, Right, now frec. This is frec r, and then we have var frec, and now frec is frec var frec r I modulo frec r size. Okay. Okay. Okay, let's see what's going on here. A mistake. What's going on here? A mistake. The error is here. Interestingly enough, we need to add 60. Or an offset. Okay. So I have various layers, sort of phase working, like a Reich style, Steve Reich style. Well, this is just very simple. So we're working with very simple objects, but the point, as usual, at least my point typically, is that when you have a formalized approach, you gain control, and control is always very important. So the control, it's better to control very simple things that not to be able to control complex things. That's my point. Of course, you might say that's an aesthetic perspective, but don't think it generally, at least in terms of designing with algorithmic composition and synthesis. Of course, if you don't control things, you can simply meet very interesting situation, but well, it's a little bit more complicated. Well, if you're very open, that's fine, but at least it can be much funny to control simple things, because you say it's a simple thing, yeah, but I can control it and do very interesting and obtain very interesting result. Okay, so fine. For this, we investigated about enveloping, and this means that we thought about the idea of time, and technically this idea of done action specification, as you have seen, is something that can convert an instrument into an event, always by using a synth. That's very, very powerful, by so to connect together sound generation and algorithmic composition.